Hi everyone, my name is Parth and I'm going to talk about delta coloring in the graph streaming model. This is based on joint work with Sepehr Assadi and Pankaj Kumar. So we'll talk about the graph coloring problem where we are given a graph G with n vertices and max degree delta, and we want to compute vertex colorings of G. So we call a coloring proper if there is no edge which is monochromatic. In general, coloring is quite hard. Like when you're trying to minimize the number of colors, then it's NP hard. And what we're interested in is computing colorings of using around delta colors. So there's a classical algorithm for delta plus one coloring, which we've all seen, which is to greedily assign colors to each vertex. So whenever you look at the vertices in any order, at any vertex, when you look at your neighbors, there's going to be one color that's not used, so you can always pick that one. And in this fashion, you can color the whole graph. We're interested in these coloring problems in the streaming setting, which is the graph is not available to you in the normal way, in the normal sense. The edges stream by one at a time, and they're in adversarial order. So you can't assume, for example, that all the edges of a single vertex would be together. And in this model, the target is to look at these one-pass n polylog n space algorithms, which we call semi-streaming algorithms. And naturally, in this talk, we're interested in semi-streaming algorithms for coloring. Which brings us to previous work in this area. So there was a breakthrough paper a few years ago from Assadi, Chen, and Khanna, which I would call ACK19. And they showed that there is a randomized semi-streaming algorithm that can compute delta plus one colorings. And more recently, and in fact, at STOC this year, there was a result that shows that this algorithm needs to be randomized. And in fact, if you force yourself to use a deterministic algorithm, then you need many more colors than delta. We're interested in getting a streaming version of Brooks' theorem, right, which is the following. Brooks' theorem says that you never need delta plus one colors, except if the graph is a clique or it's an odd cycle. And this is a classical theorem in graph theory, tons of proofs over the last century. But the one thing that all these proofs have in common is that they use some form of exploration. And what I mean by that is that they all imply algorithms which are more complicated than the simple greedy algorithm for delta plus one coloring. That is, they look beyond just the neighborhood of a vertex to decide its color. So our question is, can we find a delta coloring from a graph stream or a streaming version of Brooks' theorem? And the answer is yes. What we show is that there's a randomized semi-streaming algorithm that in one pass computes a delta coloring of the graph if it exists. And there are two ways to look at this result. One is with this lens of a new proof of Brooks' theorem, which does not use local exploration. And the other way is to, if you're simply interested in delta coloring and streaming, then this improves over the previous best approach, which was just to store the entire graph. So I'll talk a little bit about the tools that go into this result. The first tool, which I call the hammer, also called palette sparsification, is the following. At the beginning of the stream, before even looking at any of the graph, you look for each vertex, you sample a list LV of colors of size log n, and then you commit to the constraint that you're going to pick the color for each vertex from its list, right? And at the outset, this doesn't seem that useful because we just made the problem harder, right? We had free choice of our colors, and now we're restricting ourselves to LV. The upshot is that you can drop a lot of edges, right? So if there's an edge such that its endpoints have no intersection on their lists, there's no way their colors could intersect, right? So you only need to keep an edge if the colors intersect, if the palettes intersect, and at the end of the stream, you can just color this restricted graph, right? And the nice thing is that this uses much less space. So in the regime that we're interested in, R is delta, right? So this is semi-streaming space. The caveat is that this might not be completely sound, right? It's possible that G had an R coloring, and in this process of picking lists, you destroyed that coloring and it no longer exists. So this technique has been used for a lot of work recently, and starting with this delta plus 1 coloring paper, and you can see a bunch of results here. I won't talk much about them. What I wanted to talk about instead is why does this work, right? And we'll sort of do a little case study on delta plus 1 coloring. So the main tool that's used in the proof is this sparse density composition. Right? What it does is partition the graph into two regimes. The first are these sparse vertices, which have a lot of non-edges in their neighborhood. What does that mean? In this example, it's these thin red lines, right? So it's pairs of vertices in the neighborhood which don't have an edge between them. And the other half, or the other part of the other regime, is these almost cliques, right? Which are more dense, and in a nutshell, they are almost cliques. So for each vertex, I'm allowed to do epsilon delta edge additions or deletions, and I'm also allowed to add or drop epsilon delta vertices. Then I should be able to get to a delta plus 1 clique. Okay. So a quick overview of the proof of this delta plus 1 coloring algorithm. It starts with this initial one-shot coloring process. So every vertex gets a color uniformly at random from the whole palette, right? So not restricted to the lists. And then you drop any colors which clash, right? So if you look at a pair of vertices which have an edge between them and they have the same color, both of them lose it. And it turns out that this sets up the graph nicely in the sense that sparse vertices are now truly low degree, in the sense that they have many pairs of neighbors like this red pair, which both receive the color and they both receive the same color. Right? So this sort of creates a gap between the number of neighbors which are colored and the number of colors that are used. And this, it turns out, is enough to sort of greedily color all the sparse vertices. And this is restricted to the lists LV. So the hard part of this algorithm is actually to color these almost cliques, right? And the main argument here is this matching style argument. So what you do is you set up this bipartite graph. On the left side, you have the vertices of the almost clique that you're trying to color. And on the right side, you have all possible colors. And there's an edge between a vertex and a color if that color is available. So it hasn't been used in the neighborhood of this vertex yet. So you can see that a matching here certainly gives you a coloring of this almost clique in the original graph, right? But this is not quite the graph we have available to us. What we have is a sampled version of this graph where this corresponds to dropping all the edges which weren't, or dropping all the colors which weren't in the palette of subvertex. Right? And the challenge is to show that this graph has a perfect matching. Right? Good. So now the first question is that I want to ask and answer is, does palette sparsification work for us directly, right? And the answer is no. It's because of this example. This is a clique minus a single edge, right? So notice that to assign a proper coloring to this clique, these two vertices which don't have an edge between them have to receive the same color. But for this to happen with these palettes, the palettes need to intersect, right? They need to have a color that's common, and for that you need palettes of size square root delta, at which point you're not saving anything over the naive algorithm. There's also a deeper reason why palette sparsification doesn't work, and it's because it implies an algorithm that's too strong, right? So it gives you an algorithm that works on repeated edge streams. And what does that mean? That means streams where you're just allowed to put an edge twice, right? And it's a bit strange because that doesn't count towards the degree. It's just as if somebody was allowed to put the edge in, and you're supposed to just read it once in some sense. So it turns out that in the repeated edge stream model, it's not possible to distinguish a clique from a clique minus an edge, right? And this is in contrast to these previous streaming coloring algorithms, which work fine on repeated edge streams. Also, palette sparsification gives a sublinear query algorithm, right? And there's also well-known query lower bound of n delta for delta coloring. So we know for sure that there's no way this works directly. So we need a new tool, which I call a scalpel or sparse recovery. And let's see a small example. This is again the same graph. It's a clique minus an edge. And I claim that we need to identify the missing edge to color this graph, right? And how do we do it? We do it by counting the number of edges incident on each vertex, right? And clearly you can see that these two vertices at the bottom have 3 edges, so they must have the missing edge between them. And in general, this idea is able to recover k-sparse vectors. So you start with a vector in n-dimensional space, which has k non-zero entries, right? And we have in our hand a map that is linear, and it goes from n dimensions to 2k dimensions. And it allows you to recover these vectors. So if you take 2 different k-sparse vectors, they're going to map to different things under A. And for us, we're going to use it to recover these neighborhood vectors. So imagine a vector that's 1 for every vertex, for every coordinate that's my neighbor. But for us, these vectors are not that sparse, right? They're up to delta sparse, which is not that useful. But the idea is that if V is in an almost clique, right, and I know which almost clique it's inside, then I have this prior in my head that all of these other vertices of the clique are my neighbors. I just need to correct that a little bit, and that's the effective degree, and that's much smaller. So let's see another toy example. Let's say you want to color this graph, right? So what we'll have in our hand is the decomposition. So we have this prior in our head of all these cliques. Let's say that during the stream, I also compute for each vertex V the vector A times X, right? Where X is my neighborhood vector. And after the stream, since I have the decomposition now, I can compute A times the characteristic of my almost clique. Right? And since A was linear, I can then recover this purple vector, which is the difference of the two. And in this example, this is too sparse, and it's much more sparse than the other vectors involved. Right? And using this, I can then actually recover the whole graph. The problem is that I lied a little bit. The effective degree was these corrections that you need to make, right? But we, by definition, had that you have to make up to epsilon delta corrections for each vertex. And epsilon you should think of as a small constant, so it can't really fight delta, right? Which grows with n. So we need to do more things. And the lesson is that we have this big hammer, we should be using it, right? And the plan is then we'll color the sparse vertices as before, and then we'll have several phases for different types of almost cliques, and we're going to combine our ideas here. And to make things simple, to make the arguments simple, we're going to assume that you get fresh palettes for each phase, and this is fine because we'll have a constant number of phases and polylog n size palettes per phase, and overall this is going to give us semi-streaming space. So let me talk a bit more about the types of almost cliques. So the first criteria for these types is the size of the almost clique. So this the natural thing. a clique is small if it has fewer than delta less equal delta vertices. It's critical if it has exactly delta plus 1, and it's large otherwise. And the other thing that affects colorings is the number of non-edges inside. So you should think of a wholly almost clique as one that has many non-edges or holes inside. And this sort of gives you more freedom, right? Because if something is a clique, then everything needs a different color. If it has many holes, then you have more things can receive the same color. And then there's unholy almost cliques, which are the opposite. So they have very few holes, and this leads to big trouble, as we'll see here. So unholy almost cliques contain this case, where k is actually a clique, right? So imagine a delta clique, and it has some neighbors outside in this fashion. So if this happens, we're in big trouble, right? Because now this coloring cannot be extended to the rest of this clique, because the color red is blocked and delta colors are not enough to color this. Sorry, delta minus 1 colors are not enough to color this. So we make a new criteria for further distinguishing these unholy almost cliques. So we'll look at high degree neighbors outside. So we call some vertex outside a friend if it has large degree into this almost clique, precisely delta over log n. And we call it a stranger if it has fewer than that. And naturally, this gives us the definition for almost clique. So we call it almost clique friendly if it has at least one friend, and we call it lonely if it has no friends. So with these types in our mind, we can sort of revisit our plan. So the first type is these wholly almost cliques, which have many non-edges inside. And notice that this type also contains all the large almost cliques, which means we're left with unholy almost cliques of two sizes. In particular, the first size is critical unholy almost cliques. And then for the small unholy almost cliques, we need a further classification into lonely and friendly. And the main tool we'll use again is this matching argument, except the one immediate change is that now the colors on the right are only 1 through delta instead of delta plus 1. And for this talk, we will perform this quick sanity check a few times, which is that the number of vertices on the left should be less equal to the number of colors on the right. And even this is not that easy to get. So we'll come back to our plan, and the first case is these wholly almost cliques. And I'm going to skip this because the argument for this follows exactly the same way as ACK19. So I'm going to skip it for now. Which brings us to the first new case of lonely small unholy almost cliques. So to color this, we'll ask this question. Remember, the trouble with these unholy almost cliques was that if the coloring outside was adversarial, we were in big trouble. So first we ask this question, when is it adversarial really? And suppose for the moment that the vertices outside were actually colored independently of each other. Then if the graph looked like this, so imagine there was each vertex outside had only one edge inside, right? Then we are pretty good, because an event of very low probability needs to happen for things to go wrong. Which brings us to these lonely small unholy almost cliques. So what we had here was all of my neighbors outside are strangers, right? So they have small degree into this almost clique. So I need many neighbors outside to block a single color, which is great, except the vertices outside are not colored independently. So we have the sneaky solution, which is to color these almost cliques before doing sparse vertices. More concretely, we break up the algorithm. So we were doing this one-shot coloring process, and we color these almost cliques between that and sparse vertices. At this point, at this step 1.5, the coloring outside, the colors received by the vertices outside are not actually independent, but we make a proxy event for that, and that makes the argument go through. And after we set this up, we need this matching style argument again, right? And this is a bit different from the previous matching argument because now the graph that we set up is not adversarial, it has some random properties and we exploit those. So that deals with these two cases. Now we're on to critical unholy almost cliques. And so far we still haven't used the sparse recovery, right? So we'll finally see it now. So this contains the case that we were struggling with earlier, which was a clique minus an edge, right? So our strategy is going to be the same as then. We're going to try to find a non-edge inside and give its endpoints the same color. So what we're able to show is that by using this sampling sparse recovery technique, which I won't describe, it's a generalization of sparse recovery, we're able to find a vertex inside such that we know all of its neighbors and it has a non-edge. Right. So how we exploit this is we know all of its neighbors, right? So we can step out of its palette to give it a color. And the crucial thing is we're going to give it the same color as its non-neighbor, right? And we don't know all of that vertice's neighbors, so we have to stick within its palette. So what we're able to show is that there's a color in the palette which will work for both of them, and we assign it to both of them. And after this, we drop the number of vertices by 2 and the number of colors that we can use by 1. And that sort of brings balance to the picture, right? So we can use this matching argument and it turns out that the proof goes through. So, this brings us to the final case, which was this picture that we saw before, that we have a small unholy almost clique and the coloring outside is adversarial because we have these high degree neighbors and it was easy to block a color. So we're going to look at one of these friends outside and we'll argue that it needs to have at least some non-neighbors inside, right? And we're able to show with this sampling sparse recovery that with high probability, we sampled one of them and we had a sparse recovery of the right dimension available. And that means we can recover the whole neighborhood of that vertex. So far what we have is a friend and a non-neighbor inside, and we know the whole neighborhood of this highlighted vertex. So we'll do the same thing as before. We're going to look for a color in the palette of this, and we're going to try to assign it to both of them. The strange thing is that this vertex had a color already. So we're going to overwrite it and give it a new color. And this should be a bit scary because we're going to use the randomness of this palette again to say that the color exists, but the randomness was perhaps already used to give it this color, right? So how we deal with this is by making fresh palettes. And we have log n palettes roughly for each vertex. And the idea is that a vertex can serve as a friend to an almost clique at most log n times because it's consuming delta over log n of its degree. So in this process, we're picking fresh palettes, but we always have enough. So by doing that, we're able to find a color that we assign to both of them. So what did we achieve? We had this color red that was blocked for everyone. Now it's not blocked for some vertices. And we have this color orange that is now blocked for everyone else, but we used it to sort of kill this vertex. And it turns out this again bridges the gap enough that we can apply this matching argument and it'll go through. So that brings us to the end. We colored all the cases, and here's a short summary of the algorithm. We start with this one-shot coloring. Then we deal with these lonely small unholy almost cliques. Then we finally do sparse vertices and the first kind of holy almost cliques. Then we finally come to the meat of the algorithm, which is using the sparse recovery and palette sparsification together to color critical unholy almost cliques, and then even recoloring some vertices outside to finally color all these small unholy almost cliques. And that brings us to the end. So what did we see? We saw that there is a randomized algorithm which can compute data colorings from graph streams. And we saw that somehow just repeating edges in the stream takes us from this semi-streaming algorithm to an n-length space lower bound. And we saw the main algorithmic technique was that by combining sparse recovery and sparse density composition, we get some powerful tool. The open question is how far can this go? So a natural stopping point or the natural next target should be something like delta minus little o square root delta coloring, because beyond this point the problem is already NP hard. And thank you for listening. Bye.